in 6A, isopentane is an alkane. State the systematic name for isopentane. So the first thing that we have to do is we have to find our longest chain, and we number them 1, 2, 3, 4, and then we do it on the reverse way, 1, 2, 3, 4. So we know that the longest chain is going to be named butane. We can see that we have a branch, that's a carbon which is not found in the longest chain. We need to decide what position that could be in. It can either be in position 2 or position 3. We always choose the lowest number, so that would be position 2. And it's only got one carbon in its branch, so the name of this isopentane would be 2-methylbutane. 6B part 1. State the name used to describe a substance that burns to release heat energy in a combustion reaction. So we can see that it's asking to describe the substance that burns, and that is a fuel. The equation for the combustion reaction of isopentane is shown. Balance this equation. So the first thing we have to remember, what does Santa say? He says ho ho ho, which means we need to do all other elements and then hydrogen and oxygen last. So on the left hand side we're going to write our shopping list. We've got 5 carbons, we've got 12 hydrogens, and we've got 2 oxygens. On the right hand side we've got 1 carbon, 2 hydrogens and 1 oxygen. So we're going to start at the top. How many carbons do I have on the left? I've got 5. How many carbons do I have on the right? I've got 1. What do I do to 1 to get to 5? I multiply by 5, so I put a big 5 in front of the carbon dioxide. They balance, so now we can tick them off. I've got 12 hydrogens on the left hand side. I've only got 2 hydrogens in the water on the right hand side. So 2 times what gives 12? That's 6. So we put a big 6 in front of the H2O. And now that they're balanced, we can tick them off. Now at this stage we want to quantify the number of oxygens on our product side. So for the carbon dioxide I've got 2 inside the box multiplied by 5 outside the box, which gives me a total of 10 oxygens. For the water I've got 1 oxygen inside the box multiplied by 6 outside the box, which gives me 6 oxygens. So 10 plus 6 gives me a total of 16 oxygens on the product side. If I look at the left hand side, the reactant side, I've only got 2. 2 times what gives 16? 8, and that is how we balance that chemical equation. A chemist calculated the energy absorbed by water when isopentane is burned. The chemist recorded the following data. Calculate the energy in kilojoules absorbed by the water in the chemist's experiment. You may wish to use your data booklet to help you. So this is where we use our triangle. Every house can't make triangle toast. The question wants us to calculate energy, so we have to write out the equation. EH is equal to Cm delta T. We can substitute in the heat capacity of water, which can be found on the first page of your data booklet, as 4.18. We then have to use a table, and we have to find the mass of water. We can see that the mass of water heated was 200 grams. We have to change that into kilograms, so that would come out at 0.2. And then we have to find the change in temperature of the water. So we can see that the starting temperature was 23, the final temperature was 35. If we take the difference between them, that would give us a change in temperature of 12 degrees. When we pop that into our calculator, we get 10 kilojoules of energy released. Remember, we want to put that negative as it is exothermic. Complete the diagram to show an experimental setup that can be used to determine the quantity of heat energy absorbed by the water when isopentane burns. You must label your diagram. So firstly, we would have to have a tripod stand above the isopentane. On top of that, we would put a metal can with water. And to measure the temperature rise, we have to include a thermometer. A student carried out an investigation to find out how concentration affects the boiling point of sodium chloride solution. Calculate the mass in grams of solid sodium chloride, which his formula is NaCl, required to prepare 500 centimetres cubed of a 0.1 mole per litre solution. So in this question we're going to be using both triangles, but let's start with the mass triangle. Mass is equal to number of moles times GFM. Now we don't know the number of moles, but we do know how to calculate the GFM because the formula for sodium chloride has been given. So if we look up sodium, we've got 1 of those atoms times by the relative atomic mass, which is 23, which gives us 23. Chlorine, we've got 1 atom times 35.5, which will give us a total of 35.5. And when we add those up, we get the GFM of sodium chloride as 58.5 grams. So we can insert that in there. To calculate the number of moles, we have to use our NCV calculation. So we've got number of moles is equal to concentration times volume. We can insert the concentration from the equation in, which is 1.5. And to calculate the volume, it has to be in litres, and they've given us 500 centimetres cubed. So 1 litre is the same as 1,000 centimetres cubed. Put the same unit, same side, so we'll put the 500 underneath 1,000 and we'll cross multiply. 1 times 500 divided by 1,000 gives me 0.5 litres. I can insert that into my calculation, and when I put that into the calculator, I get the number of moles as 0.75. I can now put that into my mass calculation, so I'll have 0.75 times the 58.5 for the gram formula mass, which will give me a mass of 43.875 grams. Name the piece of apparatus which should be used to accurately measure the mass of sodium chloride required to make the 1.5 mole per litre solution. When we're measuring mass, we want to use an electronic balance. The student heated 3 samples of 1.5 mole per litre sodium chloride solution until they boiled and measured the temperature each time. The boiling points were 105, 107 and 108 degrees Celsius. Calculate the student's average boiling point in degrees Celsius for the 1.5 mole per litre sodium chloride solution. So to take an average, we do 105 plus 107 plus 108 divided by the number of boiling points which were taken, which was 3. And when I put that into my calculator, I get 106.666667 degrees Celsius. But what we want to do is we want to round that, and if we round that to 106.67, that will give us our average temperature for the boiling point. The student measured the boiling points for 2 more concentrations of sodium chloride solution. The average boiling point for 0.5 mole per litre was at 101.3 degrees, and the average boiling point for 1.0 mole per litre was 104.0 degrees Celsius. Present these results and your answer to B part 1 in a table. So you're going to get 1 mark for the correct headings with the correct units. So one of the headings is going to be the concentration of sodium chloride solution, and the unit we're measuring that in is mole per litre. What are we doing with that? We're calculating the average temperature or average boiling point, and that is in degrees Celsius. So you got 1 mark for those 2 headings with the correct unit. The next thing is to put your information in. So you would have 0.5 and 1 mole per litre. And in the previous question, we had 1.5 mole per litre. For the correct average boiling point, for the 0.5, we had 101.3. And for the 1 mole, we had 104. And for the previous question, whatever you got for your answer, in this case for us, it was 106.67 degrees Celsius, and those will get you your 2nd mark. State the type of graph the student should draw to present these results. So what we can see with the 2 columns is that they both have numbers, and if you've got 2 sets of number data for each column, you're wanting to use a line or a scatter graph. The student's aim was to find out how the concentration of a sodium chloride solution affects its boiling point. Suggest a conclusion for the experiment based on the student's results. So what are we doing to the concentration? We are increasing the concentration of sodium chloride solution, and what can we see from the results of the boiling point is that the boiling point increases.